In this lesson, we will discuss a specific type of series called an alternating series. An alternating series is a series whose terms are alternating between positive and negative. So here are a few examples. So for this first series, we start at 1. When you input 1, we get negative 1 to the 0 power, which is 1 divided by 1, giving us 1. When you input 2 in the numerator, you have negative 1 to the first, which means your next term is going to be negative, and the denominator is 2, so that will be minus 1/2. When you input 3, the power on the negative 1 is positive, so the numerator is positive 1, the denominator is 3. So this series will alternate 1, negative 1/2, plus 1/3, minus 1/4, plus 1/5, minus 1/6, etc. Now, in this next series, the first term is negative, so we'll have negative 1/2, inputting 1 in every place for n, plus 2/3, minus 3/4, plus 4/5, etc. To test an alternating series for convergence, we use something called the alternating series test. So suppose we have an alternating series of the form negative 1 to the n minus 1 times b sub n, and the b sub n's are bigger than 0 for all n. If the series meets these following two conditions, then the series is convergent. So the first one is that b sub n plus 1 must be less than b sub n. So this means that the sequence of b sub n's must be decreasing. And you can prove that one of two ways. You can either plug in n plus 1 and n and compare these things directly and show that this is a true inequality, or you can consider the related function f of x, where f of n equals b sub n, and look at the derivative of f. And if f prime is less than 0, that means that f is decreasing. And the other condition that must be met is that the limit of the terms must approach 0. So if the b sub n's are decreasing and the limit is 0, then the series is convergent. Let's discuss why this is true. So remember that the sum of the series is the limit of the sequence of partial sums. So our first partial sum involves only adding b sub 1. So here I start at 0 and I go over to some place b sub 1. And that is my first partial sum, S1. And then I take away b2, and since b2 is less than b1, when I go backwards, I don't end up all the way back at 0. So there's S2, this distance we moved was negative b2. And then I add on b3 and I go forwards, but not all the way to S1 because b3 is less than b2. And that will give us our third partial sum. And if we go backwards again by adding on the fourth term, there will be our S sub 4. And you can see that these even partial sums appear to be increasing, and the odd ones are decreasing, and they're increasing and decreasing to the same value, which is the sum S. So here is the formal proof of that. So we're going to consider the sequence of even partial sums. Looking at the even partial sums. So first of all, S sub 2, that's equal to b1 minus b2, and it's bigger than or equal to 0 because b2 is less than b1. And then S4, that's the same thing as taking S2 and adding on b3 and taking away b4. And this is bigger than or equal to S2 because b3 minus b4 is positive, because you know that b3 is greater than b4. So we have S4 is greater than S2, S6 will be greater than S4, So what we have now is S2 is less than or equal to S4, less than or equal to S6, etc., which means that S sub 2n, that's the even partial sums, is an increasing sequence. And it's also a bounded sequence, an increasing bounded sequence. And so it's bounded above by the first term, that's the biggest it is. So it converges to some S. Next, we must show that the odd partial sums converge to the same place. So we'll find the limit as n goes to infinity of S sub 2n plus 1. Those are the odd partial sums. Now, the 2n plus first partial sum is found by taking S sub 2n and adding on the 2n plus first term, that's the next term. And we know that the limit of this part goes to the sum of the series S. And by assumption, the second part goes to 0. So the limit of the odd partial sums is also S. So the even partial sums increase to S, and the odd ones decrease to S, and thus your series from n equals 1 to infinity, negative 1 to the n minus 1 times b sub n, that sums up to S, i.e. it converges. We're not often going to be able to determine what the series converges to, but we'll be able to determine that it does converge by the alternating series test. So determine whether the series sum from n equals 1 to infinity, negative 1 to the n minus first power over n is convergent or divergent. So we are going to let b sub n equal 1 over n, and we must show that the two conditions of the alternating series test are met if we think that this would converge. So the first thing that must be shown is that b sub n plus 1 is less than b sub n. And here is how you actually prove it. So we know that n plus 1 is greater than n, and as a result 1 over n plus 1 is less than 1 over n, and 1 over n plus 1 is the same thing as b sub n plus 1, which is less than b sub n. Now it's more or less obvious that when you increase the numerator, the size of the fraction itself becomes smaller. So in this case, it's pretty obvious that this is true, but when you add something to the numerator and the denominator, it's not quite as obvious. You'll need to use a little bit more work to prove it. So the first condition is met. Also, the limit as n goes to infinity of b sub n, that's the same thing as the limit as n goes to infinity of 1 over n, which is definitely 0. So both conditions of alternating series test are met. Thus, the sum from n equals 1 to infinity of negative 1 to the n minus 1 over n converges. And say by the, just to abbreviate, we'll say AST for alternating series test. Determine whether the series from n equals 1 to infinity, negative 1 to the n times 2n squared over 6n squared plus 1 is convergent or divergent. The decreasing can be relatively hard to determine, so what I would suggest is starting by determining if the terms limit to 0. So this is going to diverge, and the reason is check the limit as n goes to infinity of 2n squared over 6n squared plus 1. That's the same thing when you divide the numerator and denominator by n squared. 2 over 6 plus 1 over n squared, which is 1/3. So if we had let b sub n equal those terms, this limit is not equal to 0. And condition number 2 of the AST is not met. Next, let's determine whether this series is convergent or divergent. So for this one, I believe that the decreasing part is easier to prove using a derivative. So first, let's just check that the terms go to 0. So we'll let b sub n equal n squared over n cubed plus 1. The limit as n goes to infinity of n squared over n cubed plus 1 is equal to 0. So we know that the second condition is met. And now let's consider the related function f of x equals x squared over x cubed plus 1. If we can prove that f is decreasing, that means that the sequence of b sub n's will also be decreasing. So f prime of x is equal to x cubed plus 1 times 2x minus x squared times 3x squared, all over x cubed plus 1 squared. So that simplifies to 2x minus x to the 5th over x cubed plus 1 squared, or x times 2 minus x to the 4th over x squared plus 1, or x cubed plus 1 squared. Now this is going to be negative or less than 0 so long as 2 minus x to the 4th is negative, or 2 is less than x to the 4th, or x is greater than the 4th root of 2. So other than perhaps the first couple terms, but this number is in between 1 and 2, so other than perhaps the first 2 terms, the sequence of b sub n's is decreasing. So by the AST, your series is convergent. Now with the next series, it isn't obvious that this series is alternating, so your terms have to actually flip-flop between positive and negative. They can't go positive, positive, negative, positive, negative, negative, positive. They have to have a consistent pattern where one is negative, one is positive. So let's just determine what the numerators are for various n's. So for n equals 1, we get cosine of pi, which is negative 1. For n equals 2, we get cosine of 2 pi, which is 1. Then we get cosine of 3 pi, where we're back at negative 1. So another way to express the sum from n equals 1 to infinity of cosine n pi over n squared plus 1 is the same as n equals 1 to infinity of negative 1 to the n over n squared plus 1. In this case, the first term is negative, just like it was with the cosine and pi. Second term is positive. So we're going to let b sub n equal 1 over n squared plus 1. So first of all, note that the limit as n goes to infinity of the b sub n's is going to be 0. You have 1 over n squared plus 1. The denominator gets large, so the whole fraction will go to 0. And then, so that's the second condition. Now, next we have n plus 1 squared plus 1 is certainly bigger than n squared plus 1. So 1 over n plus 1 squared plus 1 is less than 1 over n squared plus 1, or b sub n plus 1 is less than b sub n. So condition 2 is met. So thus, by the AST, the sum from n equals 1 to infinity of cosine n pi over n squared plus 1 converges. It would have also worked just fine to consider the function f of x, which is 1 over x squared plus 1, and find the derivative, but since this one was pretty easy to prove directly, you can also do it this way. Let's determine whether this series is convergent or divergent. So first of all, let's start by defining what b sub n is. So we'll let b sub n equal 1 over ln of n plus 4. And the first thing to notice, I guess, is that the limit as n goes to infinity of b sub n, that's the limit as n goes to infinity, 1 over ln n plus 4. Since the natural log is an increasing function, we'll have 1 over a very large number, and this limit will go to 0. So condition 2 is met. And also, when we plug in n plus 1, we'll have ln of n plus 1 plus 4. That's certainly bigger than ln of n plus 4. So 1 over ln of n plus 1 plus 4 is less than 1 over ln n plus 4. In other words, the n plus first term is less than the nth term. So thus, by the alternating series test, the sum from n equals 1 to infinity, negative 1 to the n minus 1 over ln of n plus 4 converges. Even though it's often not possible, or at least not easy, to find the sum of an infinite series, it is easy to sum a finite number of things, say from n equals 1 to 100 or 1,000, and a good question is how accurate is that estimation? So for alternating series, there is a very easy way to estimate the remainder, or the amount that you could be off by your error. So if you have a convergent alternating series and it satisfies the condition that the n plus first term is less than the nth term, then the remainder, so how much you could be off by, its absolute value is less than or equal to a sub n plus 1, which is the next term you leave off. So here is why. So think back to that picture that we had where we started at 0 and we had s sub 1 was up here, s sub 2 was over here, and then s sub 3, and then s sub 4. So it is the case that s lies between any two successive partial sums. So we'll say s sub n and s sub n plus 1. So s is in between s3 and s4, and s is in between s1 and s2. Or it'd be between s4 and s5, because when we added on the fifth term, we'd end up over here, somewhere to the right of s. So that tells us that the total sum minus the nth partial sum, that's less than or equal to the distance between s sub n plus 1 and s sub n, and that is just b sub n plus 1. The difference between those two things is it could be positive or negative, but the absolute value, it's the next term you left off. Approximate the sum of this series by using the first 6 terms. What is the error in this estimate? So the sum is about equal to a sum from n equals 1 to 6, negative 1 to the n plus 1, multiplied by 1 over n factorial. So that will be 1 minus a half plus a sixth minus a 24th plus 1 over 120 and minus 1 over 720, and that's approximately equal to 0.6736. Now we know that the absolute value of the error is less than or equal to the absolute value of the next term, so the 7th term, which is equal to 1 over 7 factorial, or 1 over 5,040, which is approximately equal to 0.00198. Next, let's figure out how many terms we have to use to get a certain kind of accuracy. So show that this series is convergent. How many terms do we need to add to ensure that the error is less than some very small number? So first, let's just let b sub n equal 1 over n to the 6th. It's pretty obvious that b sub n plus 1 is less than b sub n, and the limit as n goes to infinity of the b sub n's is going to equal 0. So you know that the series converges. If the series doesn't converge, this remainder theorem is not true. So we need our error to be less than 0.000,1,2,3,4,5,005. And the error can be approximated by 1 over n to the 6th, so less than or equal to 0.000005, multiplied by n to the 6th. Since n to the 6th is positive, that will not change the inequality. So 1 is less than 0.000005, and 6 dividing by 0.005 we'll have 200,000 is less than n to the 6th, and taking the 6th root we'll have 7.647 is less than n. So 7 terms won't be enough, but 8 will. So we'll have, if n is greater than or equal to 8, the error will satisfy this inequality, so we need 8 terms. Which honestly doesn't seem like that much to produce this type of accuracy. That's pretty darn accurate, just 8 terms. The final definition we'll talk about is something called absolute and conditional convergence. So a series is absolutely convergent if the sum of its absolute values converges, and a series is conditionally convergent if the sum of the series converges but the absolute values do not. So an example of an absolutely convergent series would be something like the sum from n equals 1 to infinity negative 1 to the n times 1 over n squared. This series converges by the alternating series test. If you absolute value all the terms, you get the sum from n equals 1 to infinity 1 over n squared, which is a convergent p-series. So both the series and the absolute value of it converges. That's an absolutely convergent series. Now, conditionally convergent, here's an example. Early on in this lesson, we showed that the sum from n equals 1 to infinity of negative 1 to the n times 1 over n converges by the AST. But if you take the absolute value of all those terms, you get the sum from n equals 1 to infinity of 1 over n, and this diverges. So in some ways, absolute convergence is stronger than conditional convergence. So if a series converges absolutely, that means that its absolute values also converge, and that's harder to be than just converging. Now, a theorem says that if you converge absolutely, then you know that your series converges. So here is how we will prove that. First, notice that 0 is less than or equal to a sub n plus the absolute value of a sub n, which is less than or equal to 2 times the absolute value of a sub n. And this should make sense because a sub n is either positive or negative, so either these two, either this a sub n and absolute value of a sub n will add to twice a sub n, or they will cancel and add to 0. And by assumption, you know that a sub n is absolutely convergent, so if you know that this converges, then you know that the sum of twice the series also converges. So by the comparison test, or by the direct comparison test even, you know that the sum of a sub n plus the absolute value of a sub n, you know that that converges. And then what you can do is express the sum of a sub n's as the sum of a sub n plus absolute value of a sub n minus the sum of the absolute values of a sub n's. It's a difference of two convergent series. And as a result, it also converges. So thus the sum of a sub n's also converge. So let's use that theorem to show convergence of some series that have terms which are both positive and negative but don't alternate. So this series has terms that some of which are positive and some of which are negative, but they don't alternate. So first of all, let's just let a sub n equal sine n over 3 to the n. Now what you should note is that the absolute value of a sub n, which is the same thing as the absolute value of sine n over 3 to the n, that's less than or equal to 1 over 3 to the n. Sine is bounded between -1 and 1, so the greatest that sine will be is +1. And you know that the series from n equals 1 to infinity of 1 over 3 to the n converges. It's a geometric series. With r equal to 1/3. And so by the comparison test, you know that the sum of from n equals 1 to infinity absolute value sine n over 3n has to also converge. Which means that your series converges absolutely. So your original series from n equals 1 to infinity of sine n over 3 to the n also converges. Now this next series is pretty easy to show that this converges by the alternating series test. It's pretty obvious that 1 over root n plus 1 is less than 1 over root n, and it also is true that the limit as n goes to infinity of 1 over root n is equal to 0. So this series converges by the AST, but if I absolute value all the terms to check for absolute convergence, I get the sum from n equals 1 to infinity 1 over root n, which is a p series with p equals 1/2, which diverges. So p series with p equal to 1/2. So this series is conditionally convergent. Strange things happen with conditionally convergent series. So in general, you know that when you add numbers, addition is commutative and you can rearrange things and add them in different orders and get the same number. Now that is not true when you have an infinite number of things. So with a conditionally convergent series, you can rearrange the terms to make the series add to something else. This is very strange, so here's an example of how this can happen. So it can be proven that the sum of the alternating harmonic series, that this adds up to ln of 2. We're going to rearrange the series and show that it adds to a different sum. So we have that 1 minus a half plus a third minus a quarter plus a fifth minus a sixth plus a seventh, etc., minus an eighth. That adds up to ln of 2. So that I didn't prove to you. We're just going to accept that that actually happens. Now we're going to multiply everything by 1/2. So my first term is now a half. My second term is now minus a quarter plus a sixth minus an eighth plus a tenth, etc., minus a 12th. You get the idea. That's going to be equal to half of ln 2. And now I'm going to insert zeros. So we'll have 0 plus a half plus 0 minus a quarter plus 0 plus 1/6 plus 0 minus 1/8. And that hasn't changed the sum. We're still equal to 1/2 ln of 2. And now if I add the two blue equations, 1 plus 0 will be 1. The positive 1/2 and negative 1/2 will cancel. We'll have 1/3 plus 0 is a third. So that's adding those two, those two, those two. The negative 1/4 will add and give me negative 1/2. And then plus 1/5. The 1/6 cancel. I now get 1/7. And I'll have minus 2/8, so minus a quarter. And then adding the ln 2 and the 1/2 ln 2, we get 3/2 ln 2. And now all that's changed here is that 1/2 and 1/3 have switched spots. So the same terms, just in a different order. And just rearranging the order in which they were added led to the sum being 3/2 ln 2. So in general, it can be shown that if you have a sum a sub n is conditionally convergent, and you pick any random number, pick some random number, say, I don't know, b, then there is some rearrangement that adds to that number. Strange things happen with infinity, and so this is one of those examples of strange things happening.